Hello, this is a video on the work in the work you need and how to calculate Charles' law gas problems. If you have already watched one of the gas law or another gas video, specifically how you do them, how to do the calculations, you can skip over the part where I talk about the steps you need to do because you've already seen it. So, um, so if you haven't, I'd like to talk a little bit about the steps you need to follow for any gas law problem, or actually any gas problem itself. You need to have watched the overall gas problem video. And what I do is I kind of explain to you, excuse me, um, the questions you need to ask yourself about the gas problem you're doing so that you can come up with the right mathematical equation. Because there are there's actually two questions you ask yourself so you can get to the right equation. Okay, so again, if you've done that, then you in a previous video, you don't have to listen to this part. Um, Once I get to the actual equations and the problem, then you can start it up again. So the first question you ask is, how many conditions does this problem have? And what that means is, the word condition is, you have a gas container, usually a balloon, and that gas has four variables or parameters: volume, temperature, number of moles, which is N, and pressure. And I call that P1 or T1, the subscript 1 meaning the first condition. Then what you do if you have a two condition problem is you do something to the balloon. And you can see that you can know that you did something because you see action verbs like decrease, compress, cool down, heat up, leak. And what happens is then your gas is a new condition. It also has four variables: a new volume V2, T2, P2, and N2. And if you do, you have two condition problem. Or if you read the question, there is no action verbs, and all you're doing is somehow declaring or describing that gas, then it's not a two condition problem, and it's what I call a one condition problem. Okay, now this Charles law is a two condition problem, and when you have two condition problems, you actually have another question you ask yourself, which is, I have four variables. How many variables or parameters, if you want, how many variables or parameters am I holding constant? And for Charles's law, you're holding two. So therefore, there are two variables left, and there's a relationship between them. They vary by some relationship. Okay, and that's from that information, you can come up with your correct mathematical relationship. Okay. Now, if you look at the steps 3 and 4, 3 says define your variables basically, and 4 says get the right equation with x, the variable you're looking for, on one side and all other variables on the other side. Those two you can kind of, it really doesn't make a difference which one you do first. But you need both of them first before you then go to the rest, 5, 6, and 7, because then you plug in the things, your declared variables into your equation, and that will be all set up so you can just give me one answer with one more significant figure in the correct units, and then change it into the right number of significant figures with the units, and then you're done. Okay, So let's look at this Charles's law specifically. So Charles's law says that if you hold pressure and the number of moles constant, how does temperature and volume vary? And what I'm going to do, since this is an explanation, I'm going to go to the mathematical equation to describe this first and how I got it. Then I'm going to explain how I declare my variables. Usually I declare all my variables because then I can figure out what my equation is going to look like. But with this one, I'll do the equation first. So using my little analogy about students in a room acting like gas particles, or since you've done the gas demonstrations or read something or did another type of lab, you know what the relationship for Charles' law is. That when you hold volume and number of moles constant, as in, volume and, sorry, the number of moles and pressure constant for Charles's law. So that means that I keep the same number of students in the room, and I keep the number of overall hits on the wall that those students do in a given time period the same. What happens if I make them go faster, as in walk faster? So, i.e., increase my temperature. Well, what happens to the wall, the whole volume of the room, so that the hits that they do stay constant? Well, if I speed them up, okay, and I keep the volume of the room the same, the number of hits is going to increase. So therefore, what I have to do to keep the number of hits, i.e. pressure, constant, I would have to make the room bigger. So the volume would have to change or increase. So while I'm increasing temperature, I'm also have to increase the volume, which makes volume and then temperature directly proportional. And as you know, directly proportional things, to create the mathematical equation and to get the mathematical equation where your unknown variable x, or whatever the variable thing is on one side and everybody else is on the other side. When you have a direct proportion, the volume must be if the volume's on the top, the temperature must be on the bottom. Therefore, if V1's on the top, T1's going to have to be on the bottom. Or if T1's on the top, V1 has to be on the bottom. Okay? So, I want you to write it like this. Okay? And here's why. I don't want you to write it T2 over V2 is equal to T1 over V1. Okay? And here's why. First of all, I want the equation with x by itself, and in this problem, you're looking for the new temperature, which is T2. Well, of course, T2 is going to be some function of T1. It's actually going to be the ratio of the change in volumes, because that's what's changing in this question. So if you set this up, okay, how the volume change numerically changes will give you an indication of how much more or less T2 is compared to T1. So that's why I like to set it up this way. Plus, it's very easy to find all the variables, because T2 is equal to some function of T1. Well, if you know that T and V are directly proportional, if T1's on the top, V1 has to be on the bottom. And there's only one place left for V2. It's on the top. So here's my equation. Now what I have to do is I have to declare my variables. And again, if this is the first time, you hear this more than once, that this is a word problem. So usually word problems that the sentence is one condition. So this is my condition 1 usually. So it says the volume is V1 is equal to 760 millimeters. T1 is 45.7 degrees C. And as you know, you have to be in K. And if you don't know, look at the work the example of work for I think I did it in Boyle's law. Okay, so it needs to he changes the K, and then the question says decrease in the volume. So here's my V2, and I'm looking for T2. So therefore, you plug in. Now, the milliliters, the volume is in the same units. Since we're stacking in this problem the units of the volume, you don't have to have the volume in liters. They just need to be in the same units. Okay, so they need to cancel out. So you get the answer T2. Now, if you look, you must have temperature in K. Therefore, it's going to be such a big deal that if you don't, and you leave in degree C, and you do the math, you get 0 credit. You don't get any partial credit at all. Okay? So in this question, it actually doesn't ask you for specific units of temperature. So therefore, what I would do is do K, because that's what it comes out in. So your temperature is in K, okay? And then you just round to the correct number. Now, if the question wanted in degree C, you would have to add this little step underneath, because of course your answer always comes out in K from your gas law calculation, and then you needed to change it into C. How do you know that you're subtracting 273? And yes, I understand that the units aren't actually canceling there. One of the few times in which it's okay. How do you know I'm subtracting 273? Well, you know that K is always a larger number than degree C. So therefore, to get a larger number to a smaller number, you better subtract that difference, or that number difference. Okay? So therefore, you get minus 110 period, because that's you needed to put it into the units place. Okay, so that's how you calculate Charles's law. Again, most of the times I'll actually declare what kind of unit you want the answer in. If not, and this happens sometimes, if not, then do the unit that you have the least calculations for, because every time you do a calculation, there's a potential for you to make a mistake. So why would you want to create another step when you could potentially get it wrong? Okay, so that's a description of how you calculate Charles's law problems.